Okay, ladies and gentlemen, welcome. My name is Zdenek Hanzalek, and this is the next talk of the scheduling seminar. Today, I'm happy to introduce Lars Rohwedder. He works as an assistant professor in Maastricht University in Netherlands. He was invited by Jan Karel Lenstra to speak about scheduling with flow time. And previously, he was a postdoc researcher at EPFL in Ola Svensson's group. And he did his PhD in Kiel University in Germany, advised by Klaus Jensen. So please, Lars, the floor is yours.
Yes, thank you very much. And also thank you, Jan Karel, for inviting me. So let me first share my screen. Okay, yes, so the title of my talk is Recent Advances in Flow Time Scheduling, and by no means I claim to give you a comprehensive overview. So this is more on some very interesting problems that fascinate me personally, but the literature on flow time scheduling is very broad, and I will not be covering everything. Um, at the same time, let me maybe mention that this is purely theoretical. So everything that I will be talking about is just on theoretical algorithms. So I will start introducing flow time in a little bit of a vague way because I will be talking about some different variants. Later, when I go into the technical details, then I will actually introduce the problems a little bit more formally. But in general, flow time, which probably most of you have heard of, is an objective in scheduling, which is the time between a job's arrival and when it's completed. So in some sense, the waiting time. How long does a job have to wait? And if in this picture, for example, you take this blue job, then this blue job is released at some point of time. Um, it has to be processed for a specific processing time, and then it is completed. And the flow time is then just the interval or the length of the interval between when it is released and when it is completed. So this is obviously a very natural measure of quality of service in scheduling. It makes sense in a lot of practical applications. Maybe it is less common to study than, for example, just completion time metrics, but it is also interesting in the sense that it's very closely connected to completion time. So the flow time would be the same as the completion time if every job was released at 0. So a lot of times flow time actually generalizes the very well-known completion time objective. So I should also say maybe that obviously in a problem there are many jobs, so we have many flow times, and then we typically minimize some kind of trade-off between the flow times, for example, the average flow time or the maximum flow time or similar. And if you've ever worked on flow time, you will probably agree that flow time is a very challenging objective. Um, Intuitively, it is very much more complicated than optimizing a completion time. And I will give you also a little bit of an intuition next why you could say that it's more complicated or more challenging than just completion time. But as I will show in this talk, there are also some problems where maybe more surprisingly, it's actually not more difficult than completion time. And maybe one to start, what's the intuition? Why does it seem so much harder? Because take this bit vague or abstract schedule here. where we have this blue job, which is somehow processed at the end of our schedule. So this gray schedule here is not specified very clearly, but just say, let's say we are processing some jobs here, and in the end we process this blue job, and the flow time of this blue job, let's say it's fairly small because the blue job is released at this point of time, and it is completed pretty quickly afterwards. But now uh, once we have a slightly suboptimal schedule, so let's say this gray part here extends just a little bit by a small factor, then this could affect the flow time of the job quite significantly. If you compare, for example, with completion time, so if I would try to optimize the completion time of this blue job, then the completion time increased just by a small factor, maybe 10%, but the flow time here increased quite substantially in this picture by more than 100%. So already small errors can easily add up and lead to flow times getting much bigger. So some of the typical tools that we use in theoretical scheduling algorithms, for example, rounding job sizes, simply do not work with flow time. Because, for example, if you round every job size by 1%, then this would not affect the completion times typically by more than 1%. But even this small rounding could affect flow times in a schedule much more. So this is maybe the most obvious technique, just the technique of rounding processing jobs that just breaks when you um, uh, go from completion time to flow time. But of course, there are also other ideas that just do not extend from completion time to flow time. And now I will give you three more concrete problems. And again, I am going over this a bit quickly, but later on in the talk, I will actually introduce the problems with pictures and more clearly. But here, just to make some concrete points, I want to look at three problems. So one problem, which is in flow time scheduling, very famous, which is a single machine scheduling problem where you are allowed to preempt jobs and you just want to minimize the weighted sum of flow times. And this is known to be NP hard. And well, recently, a few years ago, there was a constant approximation shown for this problem. Let me know that. Let me say that I start with the state of 3 years ago to keep some tension, and I will. There will be actually new results that I will present today. But this is just for introduction, the state from 3 years ago. And anyway, this constant approximation was a quite big breakthrough for weighted sum of flow times. But if you look at the same problem with completion times, so you just replace flow time by completion time, this is still not a trivial problem, but a PTAS has been known for quite some time, and constant approximation is rather simple. Um, so here you already see maybe that it seems that a flow time in this setting is much more challenging than completion time if you just compare like a large constant approximation with a PTAS. And similar situations are in the two other problems. So the second example that I mentioned here is scheduling on identical parallel machines and minimizing the maximum flow time. So for this problem, we have for a long time three approximation, which is actually a simple greedy algorithm. And the corresponding completion time problem, which is PC max, it's a very well-known problem in scheduling, where you just want to minimize the make span on identical parallel machines. Of course, this is one of the earliest examples of PTAS, and we have known PTAS for a long, long time. And this is the typical approach of you round processing times, then you have only a constant number of processing times, and you solve this exactly, for example, with a dynamic program. And like I said earlier, this approach just doesn't work in the flow time problem. So this is why the more general problem of PRJ max does not have a PTAS at the moment. At least we don't know how to do it. And if you go from identical parallel machines to unrelated parallel machines, you again see a big gap in completion time problems. So this is the famous algorithm by Lenstra, Schmois, and Tardos for minimizing make span on unrelated parallel machines. This gives you a true approximation, a nice small constant, and for maximum flow time, we had just this logarithmic approximation. So if you look at all these three natural problems, you see that the result for flow time is much worse than for um, uh, completion time. And maybe this is what you would expect, because I explained earlier that it seems intuitively much harder. But now the surprising pattern that you can recognize here is that the lower bounds here are all the same. So the upper problems, the flow time problems, are clearly harder than the lower problems. But the only hardness we know for these flow time problems are actually what is inherited from the completion time problems. So looking at the lower bounds, there's no indication that this problem should be harder. I mean, this is a selection of three problems, and there are other examples of flow time problems which are known to be harder than completion time problems. But I find it kind of intriguing to see that in these three problems, it's not clear that we cannot achieve the same thing that we achieve for completion time. And well, now I want to talk or mention the actual progress that I will be talking about today. And the first result that I will present is that we actually achieved for the first problem for minimizing the weighted sum of flow times, we achieve a PTAS. So we match the same approximation result that is known in the completion time setting. And the second result that I want to mention is that also in the unrelated parallel machine setting for maximum flow time, we are able to somehow narrow the gap. Also here, we are improving the upper bound, coming closer to what is known for the completion time variant. And well, both of these results might at least hint at the fact that maybe we are not limited by complexity issues, but maybe we just need new tools for solving flow time problems that we haven't found so far. And so, like I said, I will start with the first problem now. And since I have only introduced it very briefly, let me give you a more careful introduction with some pictures. So our jobs, they have a processing time, they have a release time. The processing time is the width of this rectangle, and the release time is the left end. And in addition to that, the jobs have some weight, which describes how important it is. Very important job with a high weight should be completed earlier, or should have, it's more important to complete it quickly. In this problem, we have only a single machine, and we need to schedule these jobs on a single machine, and we are even allowed preemption. So, for example, we could schedule the blue job first because it's the only job that is available, and then we could start with the green job. But the purple job is more important, so it would make sense to interrupt and first process the purple job, then maybe finish the green job, and um, uh, then complete the red job. So if we have this schedule, we get a flow time for every job. So we see, for example, that the green job has a quite high flow time because we delayed it to first process the purple job. And our objective is to find a schedule that minimizes the weighted sum of flow times. So it's actually a substantial generalization of just average flow time, but still a lot of single machine problems in scheduling are fairly easy to solve. And especially if you allow preemption, this usually makes the problem even simpler. So it's quite surprising that this particular problem has been so difficult to make progress on. And I want to now summarize a bit of the last years where there has actually been very interesting progress on this problem. Like I mentioned earlier, the first constant approximation was actually a big breakthrough. This is far from trivial. It's already very complicated to even get a constant approximation. And this is due to Bhattacharya and Kumar, and the first algorithm would even run in pseudo-polynomial time, so not even in polynomial time. Then, so this is not easy to get the polynomial time algorithm, a truly polynomial time algorithm, because like I said earlier, rounding is quite difficult. So it's not even clear how to round the input in this problem, even to polynomially bounded numbers. But 1 year later, Feige, Kulkarni, and Lee actually succeeded in a, again, highly non-trivial result where they were able to reduce an instance with potentially exponential size input numbers to instances that are polynomially bounded. So if you can give a good approximation for polynom that is pseudo polynomial, you can use the result to just get a truly polynomial algorithm. And so this also led obviously to the first constant approximation in truly polynomial time. And I should mention that this constant is fairly large. It was clearly not optimized, but like in the Bhattacharya and Kumar's work, it's larger than 10,000, maybe even far larger than that. And it was also not obvious how to optimize this to something, let's say, below 100. So this was now the first work that I was directly involved in here. Together with Andy Wiese, we were able to improve the framework of Bhattacharya and Kumar to arrive at a 2 plus epsilon approximation. So now we are already in a much more pleasant area where this is actually a quite small approximation. And just very recently, last summer, together with a student, Alexander Armbruster, of a student of Andy, we managed to improve this again to get the actual PTAS. So I want to mention in particular that Alexander Armbruster came up with the main idea here towards the PTAS. So I find that very impressive for a master's student. In my talk today, I will not give you all the ideas that go into the PTAS. Actually, in order to arrive at the PTAS, it was very important that we first simplify the framework by Bartragak and Kumar significantly so that we can optimize the constants. So as a byproduct, in some sense, we achieved a much simpler constant approximation. So in this talk, I will only give you the main ideas how to get a constant approximation, and I will only hint at what is necessary to get even lower to PTAS. And all the ideas that I present are a combination of these previous works. So in my talk, I will assume that the input numbers are polynomially bounded. So this requires the framework by Feige, Kulkarni, and Lee. And the algorithm that we end up with is actually a simplification or an extension of the ideas that were already introduced by Bartragak and Kumar. So we are, to get this PTAS, we are actually starting with an integer programming formulation of the problem. And I will not go through all details of this integer program. It's more important to get a general idea of what the structure here is. This is a standard time indexed linear program where we have a variable for every job and every time t, which essentially says, has this job finished by time t, or more precisely, has this job not been finished by time t? And if you have these time index variables, then it's fairly straightforward to write the weighted sum of flow times as a linear objective. And there are two groups of constraints. The first group of constraints, and again, I will not go into detail at this moment, but it's a covering constraint, and this basically implements that your single machine has limited processing power. It says something like during each interval s to t, you cannot process more than a volume of t minus s of jobs. And the second constraint is very natural. It just says if your job has not been finished at a certain time t plus 1, then at time t, it also has not been finished. So these variables need to be somehow monotone. We are trying to approximate this integer linear program, and the main approach here is that we need to understand the structure behind it. And even though this linear program might look very complicated at first, it actually has a very surprising, very clean structure in it. And I will try to explain this next. So you can visualize it very nicely in a geometric way. And in this picture here, I have a row for every job, and I've sorted them by the release time. So the first row corresponds to the job that's been released first. The second row to the second released job, and so on. And the x-axis here, the columns correspond to the discrete time steps. And this, I can work with discrete time steps just because I can assume that the input numbers are polynomially bounded. So this integer linear program is still polynomial size. And so each of these squares, so this is any square where it corresponds to a time step after which a job was released and a job. And each of these squares corresponds to one of the variables in my integer linear program. So the integer linear program corresponds to actually selecting some of these squares. And well, the second constraint that I explained tells you that you have to select a prefix of squares of each of these rows, simply because selecting it intuitively means that the job has not been completed yet. And if it has not been completed yet at this point of time, then it also has not been completed yet at the previous point of time. So we need in this problem to select a prefix of each of these rows. And well, selecting a square has some cost associated with it, which comes from the weight of the job. The second constraint actually also has a very nice visualization in this picture. Namely, if you look at one of these covering constraints, and I will just ignore the right-hand side here, but the variables involved in one particular covering constraints, they actually all concern the same time step t. So this means that the support of this constraint is contained inside one of these columns. And if you look at it even more closely, you can actually see that the support here is exactly a prefix of a column. And the coefficient with which you multiply each of these variables corresponds to the processing time of the job corresponding to the role. So in some sense, we started with the flow time problem, and now we have a geometric problem, which is you select a prefix of each of these rows such that these constraints that are formed from prefixes of columns are all satisfied. So you need to, so if one of these prefixes of rows intersects with your constraint here, then this is this job is counted towards this covering constraint. And for each of these covering constraints, you need to have enough rows that extend until beyond this column so that you cover a certain demand. So select prefixes of rows such that prefixes of columns are covered. So this is now a geometric problem that we arrived at, but it's still a very complicated problem, and it still remains very unclear how to approach it. And to approach it, we will actually simplify this even further. And one particular aspect that makes this problem quite complicated are these prefix constraints on the rows. And we will now trade in these prefix constraints for other constraints that are somehow a lesser evil. So what we would like to do instead is we would like to group the squares inside each of these rows in some exponentially growing way. So this is the most naive way. You take the first square, then you take the next two together, the next four together, and you group them together in this way. And my constraint is now that of each of one of these groups, I have to select either all of these squares or none of them. And but I get rid of the prefix constraint. And this makes sense in the following way. If I had a solution which satisfied the prefix constraint like this, then because of this exponential grouping, I would need to extend it only by less than a factor of 2 in order to satisfy the group constraint, which says of each group select either all or none. And similarly, if I satisfy the group constraint, so I select from each group all or nothing, then I can extend it to a solution that satisfies the prefix constraint just by adding less than, basically adding a volume of less than what I already added. So in both cases, going from a solution to the of the prefix constraint to group constraint or vice versa just increases the cost by a constant. So you could say that the group constraint is up to constants equivalent to the prefix constraint. So we will now take the group constraint instead of the prefix constraint. But this still happens to be too complicated problem, because if we do this for every row, then we end up with quite complicated intersections of these group constraints. So one idea that already Bhattacharya and Kumar had was that you can define a more involved, clever exponential growing grouping, such that you also have this nice hierarchical structure in your groups. In particular, that each group that you have in some row is a subset of the group in the previous row. So this is still an exponential growth in the groups, and so the same trick works, and you still only lose a constant in this reduction. So we reduced from the prefix constraints to these group constraints with a nice hierarchical structure and lost only a constant. And of course, for the PTAS later on, we cannot afford to lose a constant, but if you define a somewhat more technically involved problem, you can actually do something similar that loses only a 1 plus epsilon factor. But for the purpose of this talk, we will just stick to the simple and clean problem. And right, so let me recap quickly. We now arrived at this geometric problem where we have rectangles that are aligned hierarchically. You could also think of it as a tree-like structure. And each rectangle has a weight and a cost. And we have these prefixes of columns. Each of them have a demand. And now we need to select a subset of the rectangles of minimal cost, such that each of these prefix demands are covered. And the prefix demand is covered if, so looking for example at this particular demand, it is covered if the intersecting rectangles that we've selected have a weight that is more than the demand of the constraint. So this is now a seemingly completely different problem, but we only lost a constant on the way to it. And the way we will solve this is actually by dynamic programming over the structure of these hierarchical rectangles. Like I said, this could be thought of as a tree, and now you look at subtrees and you do a dynamic program from the leaves upwards to the root. And a subproblem now corresponds to one rectangle and all the rectangles below it. And in the spirit of a dynamic program, we want to now determine a solution for this subproblem, and then we would also maybe determine a solution for the left subproblem, and then we would join them together. But of course, now the question is, what do I need to know in order to determine the solution of this subproblem? Because clearly, to determine which rectangles I should select here, I need to know something about the rest, because this is not, the subproblem is not independent from what I select in the remaining problem. So that's the question. What do I need to know in order to determine what the solution of this subinstance is? And if you do it naively, then you would actually need to know exactly how much of each of these constraints, of these prefix constraints, how much of them is already covered outside of my subproblem. Because if, for example, these two rectangles are selected and maybe this demand is fully covered, then I don't need to be worried about it anymore. But if they are not, then I need to cover this. So naively, the information you would need and which you would encode as dimensions in your dynamic table would be how much is covered of each of these rays outside of my subproblem. But this is too much information, because there could be linearly many such demands for which you would each need to remember some number, how much is already covered. And this would blow up your dynamic table to an exponential size, which obviously we cannot afford. So in the previous works before the PTAS, there was a lot of technical work involved, but in the PTAS we came up with a much cleaner way of doing it, and this was basically enabled by studying more closely the structure of these demands. And here I have to go back to the integer linear program and look at how the demand actually looks. And just for visualization, you have a constraint for every t and s, and you can think of t as being the column and s as being the row, and this demand, it goes from all the way to on the bottom to until s. So this is a little bit imprecise, but for intuition it will be enough. And the constraint that you have is that the rectangles that intersect with this column, that we select needs to be at least the volume of all the PJs. So this corresponds to jobs in these rows minus some constant t minus s. And now the important insight is that we can actually just break these sums apart. I will just so previously I had here a sum over all jobs with rj between s and t, and now I will just break it into two parts, rj between s and s prime and s prime to t. And as s prime I will select the upper end of my subproblem, and the same I can do for the right hand side. And what you end up with is that this red part here is actually the constraint that you get for s prime and t. So to recall, we have this kind of constraint for every s and t, and or if you take an s that goes outside of your subproblem, then you can break apart this constraint in some part which corresponds to the constraint that ends exactly at s prime, and some additional part that is denoted green here. And the interesting thing is that this green part, it does not depend on t at all. And this means that there is a certain value s which is somehow the worst case, in the sense that it makes this constraint as hard to satisfy as possible. And we only need to satisfy this constraint for t and s prime with a certain slack, which is determined by the worst case value of these green things. And this is maybe the most complicated part of this talk, but since this green part does not depend on t, all the constraints that go outside of my subproblem have the same worst case value here. They have the same worst case s. And so maybe if you didn't follow completely, but the message here is that each of these constraints that exceed beyond the subproblem, I just need to satisfy with one particular additional slack. And this is the same for all these constraints. So I just need to remember for the subproblem one value, which is how much of this worst case slack um, satisfy in addition to my constraints for t and s prime. So um, this, in the end, this just means that if you look carefully at the constraints, you can reduce the amount of information that you need to encode in your dynamic program to a single number. And then we end up with a simple dynamic program over a tree structure, which just has this one extra number encoded as a dimension. And with this approach, you can actually recover the optimal solution to this problem where we arrived at only by this simple dynamic program. And of course, the reduction to this problem itself is not lossless. Here in what I presented, you already lose a constant. And if you want to go back down to 1 plus epsilon, you need to have some additional technical work, but the main idea remains the same. So this concludes what I wanted to say about the PTAS for sum of weighted flow time on a single machine. And there's one second topic that is much shorter, where I want to go into the result of parallel identical machines, unrelated machines. So the problem setting that we have here now is RF max, which means that we have unrelated parallel machines, a much more complicated machine model. And the unrelated part here means that a job, for example, this blue one, the processing time on some machine might be completely different to the processing time on a different machine. For example, if I schedule it on the first machine, it might be much smaller. If I schedule it on the second machine, it might be much bigger. So this is somehow the most general machine model that you typically think of. And our goal is to minimize the maximum flow time. So maximum flow time, on the other hand, is somewhat simpler than some of weighted flow times. So the main intuition you need in order to think about maximum flow time is that there's one particular constraint which is necessary and sufficient for getting a certain bound on the maximum flow time. And the constraint works as follows. If you look at, so our goal is to have a maximum flow time of Fmax. Let's say this is a specific value, our objective that we want to achieve. Then we look at one particular machine and the jobs that are assigned to it. Then we want that for every interval S to T, we have that the sum of processing times of jobs that are released between S and T does not exceed T minus S plus F max. So this is very natural, because if you only look at jobs released between S and T, then clearly all of them should be completed before T plus F max, because each of these jobs is released before T. So if it was any of them was completed after this time, then it would have a flow time of more than F max. So clearly the volume of these jobs should be less than the length here, this T minus S plus F max. So quite interestingly, this condition is also sufficient. So if you assign jobs to machines, you don't even care about the actual schedule on each machine, but you satisfy this constraint for every interval, then you can guarantee that there's a schedule which has maximum flow time F max. And this idea, this condition actually leads directly to a log n approximation by doing a natural linear program. And this is essentially what the state of the art was by Bansal and Kulkarni. So their approach was to use iterative rounding. They basically implemented an assignment LP where they added the constraints that I just mentioned. And to round this, uh, the rounding procedure would actually could only round half of the variables to integer at a cost of an error of order of opt. So they increase the maximum flow time by opt around half of the variables. Then they repeat and repeat, and clearly they have to repeat it log n times. And in total, they then lose a factor of log n. And this is a very natural iterative rounding type of argument, and this log n seems to be very inherent in it. So this was also very hard uh, very hard to break this particular value, because at least in this method it seems to be very inherent. So together with Nikhil Bansal and Ola Svensson, last year we actually managed to improve this to order of square root log n. And here we have to go away from iterative rounding, because iterative rounding, at least in this form, cannot do better than log n. And we managed to get order of square root log n by relying on results from discrepancy, which is quite heavy machinery, but we are actually using black box results from there. So this is interesting not only for scheduling, because we get better guarantees for flow time scheduling, but also maybe for discrepancy, because our way of using discrepancy here actually motivates also new questions in discrepancy, because clearly we are not satisfied yet with the order square root log n. We would like to have it constant, ideally a small constant. And it seems that the key to do that is to improve maybe methods from discrepancy. So I will give you a brief overview where I, for simplicity, assume that I'm already given a half integral LP solution. So think of this as a solution to our problem, but each job can be split in half. So for example, this purple job, half of it is processed on the middle machine, half of it is processed on the top machine. And we now just want to round this half integral solution. So of course, later on, we will have any kind of fractional solution that we want to round, but as a first step, we will all just talk about half integral solution. Now, if you have a half integral solution, then there are, to round a job, there are only two natural, sensible ways. You could put all of the job on one machine, or of the job on the other machine. It doesn't really make intuitive sense to put the job on some machine where in the half integral solution it was not scheduled. So we either increase the processing time that has to be processed on the first machine by half of the job size, and decrease the second machine's volume by half of the processing time, or we do essentially the opposite. So for one job, we essentially have the option. So if you look at the volume scheduled on each machine, we have the option to either um, add this vector or subtract it. So this is a vector which has half of the processing time on the one machine where the job is assigned, minus half on the other, and zero on all others. So for each um, job, we intuitively have to decide whether to add this vector or to subtract. So this is kind of the question that arises when rounding a half integral solution. And now in the end, we want to have a small maximum flow time. And as mentioned earlier, the condition for having a small maximum flow time is that you have, for each interval, you want to bound the volume of each machine. And in you can also just take the intervals of jobs. You sort the jobs by release time, and then you look at intervals of jobs by release time, and you bound these volumes. And if you do this, what you end up with is a problem like the following. You are given vectors that correspond to jobs, of course, and these vectors are fairly small in L1 norm. So the L1 norm, the sum of all entries of the absolute values of all entries, is bounded by a small value. Essentially, you can bound it by the optimal maximum flow time with some care. And the question that arises, to get a good um, rounded solution, you want to decide signs epsilon 1 to epsilon n, either -1 or 1, such that for each interval L to H, the sum of these input vectors multiplied by the sign is bounded by some good upper bound. And this should be in each dimension, because each dimension corresponds to a machine, and in each machine we want to have a lower maximum flow time. So this sign sum should in infinity norm be rather small. So that's intuitively a kind of problem that you arrive at. And if you saw discrepancy before, then you will agree that this looks very, very much like a discrepancy problem. And it is. And there have been results for exactly this problem, or even more general problem. And one of the most fascinating results in discrepancy is that for this problem, you can actually prove a bound of square root log n times t, which is the maximum L1 norm of any of these vectors. So this improves over the easy log n that you could get for this same kind of discrepancy problem. And if you transfer these results carefully, you can use this to prove that you can round an LP solution only by losing a square root log n factor. And of course, this also works in the non-half integral case. The idea is, in sense, you start with a very fractional solution, and then you make it less fractional. So from 1/8 integral to quarter integral to half integral to integral. And if you do it carefully, you will only lose square root log n in total. So what we get are integrality bounds for maximum flow time, and you can do something similar for total flow time, although the bound here is worse, which still makes sense because the lower bound in the total flow time case is log n. So in both cases, we are square root log n away from the lower bound. And it should be mentioned that Banachek's proof is not constructive. So we actually don't get an efficient algorithm that rounds a linear program. We don't get an approximation algorithm. At this point of time, we only get a bound on the integrality gap. So this is actually an open question and discrepancy whether you can fully constructify Banachek's methods. In this case, we do not have a constructive proof of his theorem yet. And actually, it is also open whether you can prove this bound just with O of t. So it's not clear if even the square root log n in this discrepancy problem is necessary. And if you would improve the discrepancy problem, you would actually get tight bounds up to constants for both of these problems. Good. So this is to conclude my talk. So we started with the question whether good algorithms for optimizing flow time are just impossible because of some inherent hardness of maybe flow time, or just because we are lacking of the right techniques yet. And in this talk, I gave you two examples of recent works which through quite involved techniques, we actually were able to come closer to the results that were known for completion time. So this would maybe hint at that the later that we simply haven't found the right techniques yet. So I want to mention also two open questions that I find particularly intriguing. One is whether you can actually get a constant for the last problem that I mentioned. And the second is identical parallel machines, also maximum flow time. And I didn't talk much about this. I just mentioned it because it fits nicely into the same pattern of problems. And it would be very good, nice to have an improvement over the greedy algorithm that we've known for a long time. So even getting slightly below this tree approximation, I would find very fascinating. Good. So thank you very much for the attention. Let me know if there are any questions.
Okay, so please don't hesitate to ask. I will let you to unmute. I have to find the list. No. Sorry. I have difficulties. Yes, here it is. Yeah, so now you should be able to unmute. So if anybody has a question, don't hesitate to ask. If nobody comes, I may have the first notice. On slide 20, you have shown the case with parallel machines, and you assume that the task can be executed in parallel on several machines, right?
So this is so in the end, I want to execute it only on a single machine, but the approach is to define a linear programming relaxation, which essentially allows that part of it is assigned to this machine and part of the other, and then the task is to actually round it so that the job is only processed on one machine. So we start with a solution which is not feasible, which has like a job executed on several machines, and then the task is to arrive at a solution where it's only on one machine.
Okay, and you can do it in polynomial time, this rearrangement, or?
No, this is so. This is we can show that there is a way to round an LP solution to an integral solution,
I see.
which is much worse.
Okay.
But so the integrality gap is small, but we don't know how to do it constructively. Probably
Okay.
there's a way, but this seems to be still a technical issue here.
Okay, so does anybody else has a question? If this is not the case, so let me thank one more to Lars. So thank you very much for your talk. And let me inform you about the next talk, which will be given in 2 weeks. It will be given by Jacques Carlier, Nestor from Leipzig, from Sorbonne University. And he will speak on 1st of February about constructive and destructive bounds for the M-machine scheduling problem. Okay. Thank you very much for being with us, and hope to meet you in 2 weeks. Okay. Thank you, Lars, once more. Bye-bye.